Okay, so it's great to have Seth Pettie here. Seth is at the University of Michigan, a longtime algorithms researcher and working on all sorts of things, streaming algorithms, parallel algorithms, graph algorithms, lots of different kind of algorithms I probably don't know about, just all throughout. And it's great to have him here in Chicago. Take it away.
Thanks. Okay, everything I'm talking about is joint work with my former student Ding Yu Wang. And Ding Yu, I really wanted him to stay in academia. And faced with the option of academia, making a little bit of money, and plan B, making a lot of money, he chose plan B. We can forgive everyone, right? So this whole talk is about moment estimation. Okay, so the idea is you have a vector x. You can update the vector by adding increments delta to different parts of the vector. And let's just assume everything is going to be polynomially bounded for simplicity. Okay, so there's two models. You know, if you only do positive updates, it's incremental. And if you allow subtractions, you can, it's called the turnstile model. Okay. So let's say at the end of this process, you want to know what the pth moment of this vector is. Okay, so you take the absolute value of all the entries, raise them to the pth power. That's the quantity that you want to estimate. Okay, so this has seen a lot of work. You just change the value of p and you get a new problem. Okay, so when we set p equals 2, the Alain Matthias Szegedy AMS sketch is, solves this problem in a very elegant way, and polynomial in log n bits and polynomial in your approximation error.
So each update's updating a single coordinate. Is that right?
Yeah, but the estimation really just says, after all the updates are done, tell me what the second moment is.
Think of delta. Should I think of delta as being one?
It's fine to say delta's 1. 1, or if you allow subtractions, -1.
It's like counting, like the usual of counting things, or yeah.
Yeah. Okay, so if you want p to be not 2, Indic basically came up with a variation on the same theme of AMS, and show that you can get pth moments, for other values of p. And p equals 0 is sort of a special case. You're basically just measuring the number of non-zeros in the vector. Or in the incremental model, you can think of this as saying, estimating the cardinality of a multiset where you might have seen elements different numbers of times. Okay, and this is a very classic sketch from the 80s. Flageolet Martin does p0. You knew how to do this at least since 1983. And there's other ways to do p0 when you have increments and decrements. There's many different ways to do this. Okay. And what are the limits of all this? So basically, if you set p to be bigger than 2, you can sketch it, but you can't sketch it in a reasonable amount of space. But I'm saying reasonable in this model is polylog n bits. Okay. So this whole talk is about the f moment estimation problem, where you have some function f, and you want to compute the sum of f applied to every part of the vector. So you can ask, based on whatever properties of this function f is this moment, tractable in the sense that I can compute an arbitrarily good approximation in polynomial in epsilon log n. And if you ever resolve the tractability question, then whatever this set t is it'll be well defined. And then you could ask at that point the universality question, which is okay, I have a large set of f's that are tractable. Do I need one sketch for every f, or can I have one sketch that just sort of magically works for every f in this entire class? Call that the universality question.
I missed. So the notion of estimation is that additive?
Purely multiplicative.
Multiplicative. So if the correct answer is small, then
yeah.
So for instance, if you have additions and subtractions and the correct answer is 0, you better give 0.
Right. Yeah. That is important. Yeah, so I guess the highlight of this, or the overview of this talk is I'm going to give a new way to sort of approach this tractability question and the universality question. And at the same time, what this work does is kind of subsumes the last 40 years of work in this area. So I wanted to show sort of some of the highlights of what we're going to subsume. So how does the AMS sketch work? So the AMS sketch is super simple. You have your vector on top, let's say, And all you need to do is maintain the inner product of your vector with a random sign vector. Okay, so you generate your random signs. Let's say, for this, everything, I'm talking about, I'm not going to talk about KY's independence. I would just say whenever something's random, it's independent and uniformly random. Okay, so you have this random sign vector, and you keep track of this sum here. So in this particular case, some of these coefficients get multiplied by -1, some get multiplied by 1. In this case, A stores the number 2. Okay, and it's fairly easy to show, there's like a 2-line proof, that the expected value of A squared is exactly the target function that we care about, okay? Because whenever you take the product of 2 different signs, as expectation 0 cancels out. And the same signs, their product is 1. Okay, so here, the correct answer is 166 in this case, and we guessed 4, and this has the correct expectation, so we can't do better than that. So obviously, the reason this is such a horrible approximation is, the variance is kind of large. So just because you have an unbiased estimator doesn't necessarily give you anything. So you do the standard stuff, take a bunch of trials, take 100 trials, you average them together, now you're talking 10% error. Okay. So this is mid-90s, let's say. Okay, so about 5 or 6 years after this, Indic generalized this to other, moments, p moments for p between 0 and 2. And basically all he changed here is you don't need random signs, you need random p-stable random variables. Okay, and p-stable random variables have this property that they give you exactly what you want. So when you take the inner product of x with a bunch of independent p-stable random variables, this has the same distribution as your target function, essentially multiplied by a single p-stable random variable. Okay, and from this you can recover an estimate for your target function. Okay, so these use, this is basically, both of these sketches just use random projection. That's the only technique. Okay, and other sketches use subsampling sort of as a technique. And a classic example of this is Flageolet-Martin. Okay, so what does Flageolet-Martin do? So Flageolet-Martin says every element that comes in, we're going to hash it to a random value. And I'll give a visual description of what this hash function is. So imagine you have a dartboard. And this dartboard has unit area, and you chop it up into m columns, equal width columns. In each column you chop up on a geometric, log 2 geometric scale. And the hash function just picks a random point in this dartboard, and the hash value is the cell that dart landed in. Okay, so J is sort of the column index, and K is the row index. Okay, and the Flageolet-Martin sketch just says, tell me which cells are occupied. Tell me which cells had darts in them. Okay, and obviously if you see the same element twice, if you increment the same part of the vector twice, you're just going to throw a dart at the same cell, and it's not going to change anything. So this is only sensitive to the number of distinct things that you've seen in an incremental sense. Okay. And you can estimate the number of non-zeros in this vector by basically just looking at the pattern of occupied cells. Okay, so obviously the ones at the bottom of the lower rows are going to be nearly completely occupied, and the upper ones are going to be nearly completely unoccupied. And you just have to find a row where, let's say, between 20 and 80% are occupied, and those rows will give you a good indicator of what the true cardinality is. Okay, and it doesn't really work for the turnstile model because you can't do subtractions. You can't, a cell has been hit by a dart, or maybe 5. So if you can't really do subtractions and guess, how many times it's been hit. Okay. So this is incremental only. Okay, so King, Nelson, and Woodruff basically took a twist on the same idea. They did this sort of the natural thing, which is, okay, in each cell, let's keep the sum of all of the parts of the vector that get hashed to that cell. Okay, and if you do that, whenever you see a non-zero cell, you know it's been hit, and whenever you see a 0 cell, it may not have been hit, or may be a false 0. Okay, so this idea by itself is not going to actually do it for you, just keeping track of the sum. But what they do is they say, suppose that we kept track of the sum mod p. P is a random prime that's sufficiently large. And we took each element of the vector and we multiplied it by a random number mod p. Okay, and if you do this, it's fairly easy to show that you're not going to get very many false zeros. You're going to get extremely few cells that, where when you take these random sums, they look like they're zero, but in fact they've been hit and they actually shouldn't be, they're not formally zero. Okay, so this is a sketch that it sort of combines the idea of subsampling. So you're kind of sampling at various levels in this sort of a hierarchy here, and also random projection since you're multiplying by these random values mod p. Okay, and to some extent, these are really the only two techniques that people use in this subsampling and random projection. Okay, so this tractability and universality question was basically defined by Braverman and Ostrovsky, and they gave a perfect characterization of every function that's tractable and non-decreasing. Okay, and at the same time they answered the universality question for this class. They basically said, and if you give me one of these functions, I have a single sketch, and it can estimate any function in this class. Okay, and it's based on sampling. Okay, so they basically sample a bunch of entries, and once you sample these entries of x, you can evaluate the function f on it after you find whatever function you care about. And that seems to be a very natural way to get to universality. Okay. And I won't say much about this, but Braverman, Chestnut, Woodruff, and Yang, they built off of Braverman and Ostrovsky and basically an almost complete characterization of the class of tractable Fs. And they gave a specific sketch for dealing with this almost complete characterization. And there's some functions that their system can't handle. They can't handle what they call nearly periodic functions. I'll get back to that later on. Okay, so the first thing I'm going to show is basically a different approach to the tractability. So these approaches to tractability basically list like 4 or 5 properties that your function should or should not have. Okay, if it grows too much faster than quadratic, you're out. If it does weird stuff like occasionally gets really close to 0, you can't do stuff like that. Okay, so it's just a list of properties essentially, and it's hard to reason about the implications of those properties. Okay, so the approach I'm going to show you is a way of building sketches in sort of a mechanical, automated way using the theory of Levy processes. So, what is a Levy process? A Levy process is basically a memoryless. X is a random variable that evolves with time t. Okay, and Levy processes are those random variables where the evolution doesn't care what time it is and is memoryless. Okay, so stationary increments. That means what happens in the next unit of time is independent of the time. Okay, independent increments, saying if you chop time up into units and you say whatever happens inside each unit are all independent. Okay, and stochastic continuity basically says that the process X itself might be discontinuous. It can go along and then it can just randomly jump. Okay, but if you look at the probability as you shrink the period of time close to 0, the probability that you see any positive jump also goes to 0. So in a sort of stochastic sense, it's continuous. Okay, so there's a lot of Levy processes you can come up with. You could say maybe it's not random. Maybe it just drifts. Okay, it just it's on some trajectory, and you measure the time, and you know exactly where it's going to be. It's going to be off in some direction gamma, and you know where it is going to be at time t. It's going to be at position gamma times t. Not a very interesting Levy process, but it is one. Maybe the most famous one is Brownian motion. So if you just take a continuous random walk, this satisfies all the properties. It's memoryless, it's independent, and so forth. Okay, you could have a Poisson process. Poisson process basically says your process is a counter. It starts off at 0, and it gets incremented to 1, and then 2, and then 3, and then 4. And the time between increments is going to be some exponentially distributed random variable, so it's memoryless. The actual timing of the increments is memoryless. Okay, and then there's some more exotic things called alpha stable processes, and I'm not going to get into that just yet. Okay, so you can have sorts of visualizations of what's going on here. So the Brownian motion, no matter how much you zoom in on this on this process here, you're going to see it's self-similar. You know, the picture will look identical to this at any zoom factor. This is a Cauchy process. It's a one-stable process. This is very interesting. So it may look like it's kind of doing something continuous here. It's not. This is taking discrete jumps at every scale, and it's also self-similar. So no matter how much you zoom in, it's going to look like a cloud of discrete jumps that get smaller and smaller and smaller the finer you zoom in. Okay, and then you have a Poisson process, which looks more predictable. Okay, so how is this connected to functions that we care about? So it turns out that each Levy process can be identified with its characteristic exponent. Okay, and what I mean by this is that if you look at the characteristic function of the process, so e to the I times z, z is your parameter, times this process at time t, the expectation of this will be something, in the exponent, something linear in time times something that depends only on z. Okay, and whatever this is, this function f of x, this is called the characteristic exponent of the process. Okay, so for some examples here, in terms of, so Brownian motion, the characteristic exponent is proportional to z squared. For Cauchy processes, it's proportional to the absolute value. Poisson, something else. Okay. Okay, and interestingly enough, these are, each of these functions here is kind of, something that we knew that was sketchable. Okay, so there is some, sort of association between the exponents that you're likely to see from Levy processes and functions that we did know were sketchable. Okay, so this is the generic method that we have to build a sketch starting for the target function that we want to sketch. So we have an f in mind. We have an f in mind that's like, this is the f moment we want to compute. And f can have some interesting structure. So the first thing that we do is we go find a Levy process whose characteristic exponent is exactly the function that we're trying to estimate. Okay, and if you can find if you can't find such a Levy process, we have other ways of doing this. This is like this Groucho Marx quote, these are my principles. If you don't like them, I have others. Okay, so for the time being, if you can't finish step one, don't go to step two. But let's say you can finish step one. You found your Levy process. So now we're going to do something similar to what AMS does. AMS picks a vector of random signs. We're going to pick a vector of random independent versions of this Levy process. Every coordinate gets its own Levy process. They're all distributed identically, but they're all independent. And now we do the exact same thing that AMS does. You take the inner product of the vector that you're sketching and the Levy process, where you measure the Levy processes at some time t. I'm going to say what t is later. Okay, we're going to be taking this and we're going to be, exponentiating in I times this, so we don't need to maintain the sum exactly. We can just maintain whatever the sum is mod 2 pi, because that's all we're going to care about. Okay, so what happens when you take this single cell synopsis of the entire vector and you look at the expectation of e to the I ct? Now we're just basically applying the definition of the characteristic exponent. Okay, so by independence, we can take this expectation of an exponential and just look at the product of a bunch of individual expectations, and then this we can apply the characteristic exponent identity to this exactly. Okay, and we'll get f of x of j. Okay, and now the sum of the x of f of j's is now going to show up in the exponent. Okay, so we have this random variable ct, and when you manipulate it in this way, it gives you, in some sense, an unbiased estimator for the exact quantity that you care about, f of x. Okay, so I'm just moving over here. So if you look at this for a second, you don't want to pick t crazy small, because this thing is just going to be 1. Okay, and if you pick t to be way too large, this thing is going to be 0. Okay, and both of these quantities are not going to, tell you much about f of x. So in order to, statistically to get some interesting information out of this, you want to pick a t that's sort of inversely proportional to the magnitude of that. Okay, and if you do that, then you have something that you can actually take the average of and calculate its variance, and then generate an approximation of. And I won't say that process, but the whole point is when you pick the proper t here, it really does give you useful information about the f moment. So what does the Levy tower do? Obviously you don't know the correct t, but if you know that like the f moment is going to be in some polynomial range, you just choose the logarithmic number of exponentially spaced t's, and you store one of these cells for each of those. Okay, great. And this gives you an unbiased estimator, and then you need to replicate it, some number of times depending on epsilon and delta if you want some kind of epsilon delta guarantee. Okay. Just like AMS, just like every other sketch. Okay. And there's a version of this for stable moments. If f happens to be a stable moment, then you don't need to do the thing with the exponentially distributed values for t, because these stable processes look the same at every time scale. So you're not actually getting new information when you measure at different t's. You can just pick a single t, and that suffices for stable sketches. So you lose a log factor there, and that helps the space. Okay. So one thing I like about this is, in a forward-looking sense, it'll allow us to prove some new things. But in a backward-looking sense, it basically gives a whole lot of explanatory power, because we can sort of explain why the world is the way it is. So in a very literal sense, like the Levy stable sketch just completely recreates index as is. That means it's not one iota different. It recreates AMS sketch in the limit. Okay, in the following sense. So suppose you have your vector x of length n, and I just extend it to be of length w times n, and I just copy whatever that vector is w times. Okay, so I've blown up the f moment by a factor of w, but I haven't really changed the vector in a substantive way. Okay, so when I apply AMS sketch to this new vector, instead of each thing being associated with a random sign, it's now associated with a sum of random signs here. And as you let w, get large here, this will just converge to some normally distributed random variable. Okay, and sampling the Brownian motion Levy process at a certain time is basically just giving you this, normal variable coefficient in front of xj. Okay, so in the limit, basically this recreates the AMS sketch. Okay, it also recreates the Flageolet-Martin sketch and its sort of successor, the hyperlog-log sketch, both for the incremental model, and it also recreates Kane-Nelson-Woodruff sketch. Okay, and I'll explain one of these. I'll do the Flageolet-Martin hyperlog-log because that shows something interesting about Levy processes. So this should seem a little bit fishy because the Levy tower by its construction is linear. Okay, you're just keeping the inner product of this and that, and if you can do an addition, you can just do a subtraction and undo the sketch and pull it back to its previous state. Okay, but Flageolet-Martin only works in the incremental model. Okay, so it would be very weird if the Levy tower explained what was going on, because it just seems like there's a fundamental incompatibility in the models. So it turns out that there are Levy processes that sort of correspond to the incremental model. Okay, you can have a Levy process that goes to infinity. So in a memoryless sense, it's just wandering around, and then it just memorylessly dies. And when it dies, it goes to infinity and stays there. Okay, so this is called killing the process. And you can think of a process called a pure killed process. A pure killed process is just 0, and then it dies, and then it goes to infinity. Okay, and when does it go to infinity? It's just after some period of time that's an exponentially distributed variable. Okay, so these are Levy processes. They're sort of degenerate in some sense, but they sort of capture what's going on in the incremental model, which is once you go to infinity, you cannot undo this operation. There's no way to subtract an infinity and get back to whatever finite value you have. Okay, so when you look at the Flageolet-Martin sketch, what you can do is think of each cell being associated with the Levy process, and you're measuring the Levy process at a time that is proportional to the size of the cell. okay? So in other words, you know, if you measure a pure killed process at time 100, it's almost certainly dead by then. And if you measure a Levy process at time, you know, 0.25, it's almost certainly still alive. So if you're, you know, if you have a, you know, 1,000 non-zero vectors, non-zeros in your vector, and you measure this Levy process at time 1 over 1,000, you're right at the point where it's informative whether the Levy process has died or not by then, according to any of these, you know, Levy processes. Okay, so that's basically what's going on here. Every cell in the entire sketch is controlled by a different Levy process in Flageolet-Martin. And if you couple them in a different way, so if you basically say there's one Levy process for the entire column and we're just measuring the same Levy process at different moments in time for these cells, this recreates the hyperlog-log sketch. Okay. So what you see in the hyperlog-log is basically, this is like, you know, this has been hit, there's a prefix of cells that have been hit, and then after that there's a suffix of cells that have not been hit, because you measured the Levy process at, you know, before it died, basically. Okay. All good so far? Okay. I've been postponing the following slide for as long as possible. So you ask, what are the forms that these characteristic exponents can possibly take? For Levy processes, this is controlled by the Levy-Khintchine representation theorem, and it's a little bit ugly. It's hard to parse at first, and you're just like, well, you know, okay, what functions could I build out of this? Okay, so let me just walk through what's going on here. There's basically only 3 or maybe 4 things going on here. Okay, and it corresponds to all the intuitive processes that we've seen before. Basically, they're saying you can't. There's no 11th type of Levy process. There's just a few types of Levy processes. So every Levy process is sort of a linear combination of something that looks like a Gaussian random walk, something that looks like a linear drift, and then the most interesting part is some mixture of Poisson processes. Okay, so you can have Poisson processes where S here, what you're integrating over, S here is controlling the jump size. So you can have processes that wait a certain amount of time memorylessly and then jump by S or jump by minus S. You know, you can have positive jumps, negative jumps, and this is just saying you can have some arbitrary linear mixture of these Poisson processes going on simultaneously. Okay, and those are basically the only 3 phenomena. Okay, so the stable moments that you see are basically formed exclusively from this mixture of Poisson processes. That's why they consist of these discrete jumps at every possible scale. Okay, so when you have these stable processes here, they're putting a lot of mass in the area around 0. Okay, you can extend Levy processes to higher dimensions, and the form of the Levy-Khintchine representation theorem stays the same, except you just replace all the everything with inner products, basically. Okay, so when you do this, the Levy tower doesn't need to change. Okay, so if you receive an update, so if each entry of your vector now is not a single real, it is a d-dimensional object, and you can give any updates you want to that d-dimensional object. Okay, so in the Levy process now, you maintain the sum of these inner products here, and everything stays the same. Okay, you still have this property here that when you take this cell and you you exponentiate I times this cell, you get something that is controlled by your target function, f of x. And basically, this lets us do a lot of different things. So it turns out we can estimate any stable multidimensional function. Okay, and we can estimate it in a very nice way, in fact, where we don't need a new estimator. So what we basically showed is when you run the Levy stable sketch, the distribution of the final state is identical to index sketch for the same value of the f moment. Okay, so any estimator that you had for index sketch, you could just apply to this one right out of the box. You can use the same code. You can also do a bunch of other weird things. You can do heterogeneous f moments. You can say every part of your vector, I care about you know, a different alpha moment. You know, this one I care about, you know, whether it's non-zero or not. This one I care about the second moment. This one I care about the first. You can just do that across the entire vector, and this sketch will still estimate that. It doesn't need to do anything special to kind of think about all these different values of alpha. Okay, so I'll go back to this slide here. So the problem with the previous one is it couldn't handle nearly periodic functions. You might say, why do you care about nearly periodic functions? You know, it turns out it's a very interesting and useful class. So let me show you something that simplifies our discussion a little bit. If you look at this mess here and you say, yes, but suppose this exponent were in fact a real function, all the imaginary parts have to cancel. Okay, so what this implies is that the Levy measure has to be symmetric if this whole thing is to be real, symmetric for, you know, positive and negative values. What this implies that the signs cancel in this expression for, you know, here. This implies that this part cancels and that there's no drift, and the Gaussian part sticks around. So when you have a real function, you can express it as the Gaussian part, z squared, and the mixture of these functions in this 1 minus cosine basis. Okay. And this is, you know, a much simplified form. So if you have a nearly periodic function like this one, this is the function they came up with, where they're like, we can't prove it's not sketchable, and in fact it is. They came up with a sort of ad hoc sketch for this, but they're like, every, you know, generic technique that we're going to throw at solving this problem is going to fail for this function because it's very weird. Okay, so tau is the position of the least significant one in the binary representation of z. And the f moment, GMP plays the role of f here. So the f moment GMP that we care about says the value of an entry in this vector is 2 to the minus this quantity tau. Okay, so this function looks like this. It wiggles a lot. Okay, it goes, you know, 1, 1/2, 1, 1/4, 1, 1/2, 1, 1/8, blah blah blah. And occasionally, you know, it gets really, 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 for large values of z, it gets really, really, really close to 0. Okay, so any kind of sampling strategy is going to fail. Whenever you sample entries, you could sample random entries, you could sample really large entries. All of those might just lead you to sample values that are really tiny, and there could be, you know, a huge value somewhere that you missed, and, you know, you would never know. So there's really no good way to compute the GMP moment of a vector with sampling. Nonetheless, they came up with a pretty complicated ad hoc way to do it. And the Levy tower just does this naturally. So one way you can see how the Levy tower does this naturally is you could say, you know, we only care about entries in a polynomial range. So let's say this polynomial is like, you know, w bits. So we're looking at entries between -2 to the w to the w. And by taking the Fourier transform of this function, we can actually write out an explicit form of this GMP function in the 1 minus cosine basis. Okay? And these, this representation of the function basically tells you, if you look at the coefficients here, they tell you what the mixture of Poisson processes are in the corresponding Levy process. Okay, so this, once you have a representation of the form like this, you can recover what the Levy process must have looked like, because it's a symmetric compound Poisson process, and you know, you can go back and you can design a Levy tower sketch specifically for this function.
So, question. So, what are like exact like periodic functions?
Exactly periodic?
Yeah.
Those are in some sense easier. Whatever the period is, it's some finite number that's independent of the size of the sketch, so it's constant. And those turn out to be easier.
I see.
Yeah.
Is there anything special about the 2 here? For example, if you replace the 2 by a 3 or another prime?
The 2 by a 3? No. This is just an example of a way to build a nearly periodic function. I mean, there's lots of nearly periodic functions you could come up with. Yeah, okay, so the Levy tower, it uses a certain number of bits. It can handle one-dimensional moments. It can handle these moments, you know, for f where it's d-dimensional. The stable is a log factor cheaper, so it's nice. And it compares favorably with the previous approach. But you might want to say, okay, what is, both of these two approaches handle the vast, majority of interesting, moments that you might want to sketch. All the standard, Keith moment things. You can do other, funny functions and so forth. And I guess the interesting action is sort of what's happening in the symmetric difference of these two approaches. And, if we're going to claim that the Levy-Tower approach is sort of the final answer to tractability, then there should be nothing in the symmetric difference on the other side, right? So we know of a couple things you can do here. You can do nearly periodic moments. You can do multi-dimensional moments. And for the other side, we don't have any specific candidates, okay? And I'll show you some efforts that we come up with to try to come up with some candidates. And you kind of need to do a little fix to be able to put some functions in that that seem to appear in that side of the symmetric difference, which in fact are actually representable. Okay, so here's the nitty-gritty details of how you make non-Levy-Khintchine representable functions basically be nonetheless sketchable with Levy-Khintchine representable functions. So this is basically, this little fact follows basically because locally the cosine function does not grow faster than quadratic. Okay, so f of beta x is less than beta squared times f of x if f is Levy-Khintchine representable. Okay, so consider this function here. Okay, you have your vector. If you see a 1 or a minus 1, you want that to count for 1. If you see any other non-zero value, you want it to count for 5. I'm going to sum this up and estimate the quantity. Okay, it's a simple function. You can obviously estimate this with sampling, so it can't be hard. Okay, but nonetheless, you can't. This function is not Levy-Khintchine representable because this fact here. It says f of 2. F of 2 can't be more than 2 squared times f of 1, but it is. Okay, so we're screwed. Basically. We came up with a simple function that kind of just breaks the whole thing, the whole conjecture. Okay, so what do we do with this situation? Okay, so here we'll have what we call the Fourier-Hahn-Levy method, and it's a way to fix this problem and other problems. So let's say we have a function that's real and symmetric and it's 0 at 0. These are like the basic properties that we need to satisfy for it to be sketchable. So whenever you have a function in this form, you can compute its Fourier transform over some large, cyclic domain here, and write it in this 1 minus cosine basis with these various coefficients. Okay? So if you look at these coefficients here, and they're all positive, then that means that it's Levy-Khintchine representable, and this corresponds to a particular compound Poisson process. Okay? If you look at these coefficients and you see a mixture of positive and negative values, then this is, in some sense, proof that it's not Levy-Khintchine representable. Okay, so step 2. You take f hat and you separate it into the positive and negative coefficients. So f minus hat is the negation of the negative coefficients. Okay. You compute the inverse Fourier transforms, and now of f plus hat and f minus hat. So now you can, this is linear transform, so you could express f as the difference between two functions. And each of these two functions is now Levy-Khintchine representable. You build the Levy-Tower for each. You estimate this, you subtract them, then you get your unbiased estimate for f. Okay. Now, the problem with this is, when you estimate this, your error is proportional to f plus. When you estimate f minus, your error is proportional to f minus. So therefore, your error is now proportional to the sum of these two things, not to f itself. This is where the dangerous part comes in. Okay. So what is this f? When f is the 0, 1, 5 function, let's say, I just picked a random domain size of like n equals 100. Okay. So in other words, I should say this. So what is absolute value when you're looking at something cyclic like this? So absolute value of x is either x or 100 minus x. Okay, so f of 99 in this case is 1, f of 98 is 5, etc., etc. Okay, so nonetheless, this is some periodic function. And the target function is the black one, and it's the difference between these two Levy-Khintchine representable functions, the green one and the red one. Okay, and in this case, the sum of the green and the red is not that bad. It's some constant factor bigger than the target function. So any sketch that you have that takes the green one minus the red one is still going to give you a very good epsilon approximation. Okay. Everyone like this example? Yeah. Okay. I have an even better one. Okay. So something really interesting happens when you try to do this for functions that grow faster than quadratic. Okay, so p moments with p greater than 2 are intractable, but what if you just try to go like a smidge above 2? Not that much. Not any positive constant, just x squared log x essentially. Okay, so this function is symmetric obviously, and it's 0 at 0, so it satisfies all the basic properties. And there's no reason why we couldn't apply Fourier-Hahn-Levy, so let's do it. And when you apply Fourier-Hahn-Levy directly to this function, remember the absolute value of x is the difference between the minimum of x and, in this case, 100 minus x. So this function is going to be symmetric around 50, and we're basically saying, the area between 0 and 50 behaves like our target function. And after this, it's going to behave strangely, but we need to set 100 to be bigger than twice the value of any thing we'll ever encounter in our vector. Okay, so yeah, so the black one's the target function. It's the difference between the green and the red. And if you sum up the green and the red here, it's a constant times the target function. But as you get down to 0 here, it just blows up. It's hundreds of times larger. Okay, so this is sort of a defective decomposition in some sense. Okay. So we could try again. There's multiple ways to do this actually, so we could try again. We could say, okay, let's take this this function f of x, and we want to pull out the biggest quadratic component of this and just look at the residual. Okay, so the largest this log term is ever going to get is, if we assume that the absolute value of x is bounded by n, the largest this is ever going to get is log 1 plus n. So let's just take x squared times log 1 plus n and set it aside. That function's Levy-Khintchine representable because log 1 plus n is now a constant. It's just x squared times a constant. Okay, and then you subtract off, the difference to your target function, and now this thing grows slightly less than quadratic. Okay, so you can do this Levy-Khintchine thing here, where you apply the Fourier-Hahn-Levy method to G, and then kind of reassemble two, functions f plus and f minus, like that. So this is sort of the decomposition of G, and when you look at the corresponding decomposition of f, now the black function is our target function. It's the difference between the green and the orange, and now the green and the orange looks like it's barely more than the black function. And it is, in fact, barely more than the black function, pretty much over the entire range, except when you get too small, and then it just falls apart again. Okay, and I can kind of zoom in on the part where it falls apart. So in other words, when the value in your vector is 5 or more, it's a great approximation, and then as you push it down to 1, it just becomes enormous. Okay, so the multiplier here is like 150, and the domain size was 100. 150 is really n. Okay, you're paying an n factor when these things get too small. Okay, this is my second try. Okay. I have a third try. Okay, so the third try is, the mistake that we're making is I have a target function and I'm trying to find a Levy-Khintchine representation of this target function that's exact, which is overkill because we're just going to end up approximating it anyway. What I really want is to take f, find an approximation of f, and then decompose that approximation in some nice way. Okay, so what I really want is take G to be a 1 plus or minus epsilon approximation of f, decompose G into some positive and negative Levy-Khintchine representable functions, and the property that I want is that the error is proportional to these G's now, and I want the ratio of this to the true value of f to be as small as possible. I want to minimize rho. Okay. And I don't know how to do this analytically, but I do know how to do linear programming, so I just did this with linear programming basically. So come up with a bunch of frequencies, omega, that are fairly dense. So for this example here, choosing the frequencies that we care about to be 1 plus epsilon to various powers is enough. Then we have here the UK's variables are going to be the positive coefficients of G plus. The VK variables are the negative coefficients, so they'll be the positive coefficients of G minus. And now I just have to set up a linear programming saying I get all the properties I want. So the first set of constraints is G is a good approximation. And the second set of constraints says that the sum of the G's is at most a rho factor bigger than the F. And the whole LP is just minimize rho subject to these constraints. Okay. Good. Okay, so in these experiments here, I can get epsilon to be really, really small. So epsilon here is like 0.3%. So the function f and its approximation over the whole domain are pretty much indistinguishable. When you look at a macro scale, our target function, the black, is the difference between blue and red, and they look like they're all pretty comparable. Even when you zoom in, so this is the range between 1 and 3. Even when you zoom in, and you get down to 1 here, so this is our target function. It's fairly close to 0, and it's the difference between the red and the black, which are a lot more, but not a whole lot more. I mean, this multiplier here, this worst case multiplier, is actually not very big. And it gets, I think it's about 18 or 19. Okay, and the range here is 1,000, and so this number is, I don't know what it is, as a function of epsilon and log n. It should be a function of epsilon and log n, and I don't know what it is, but it's very reasonable, whatever it is. Okay. So, all right. So this, I think, is a good enough tentative evidence that, like, there's some way to, if you find a tractable function, there's some way to rejigger the Levy-Tower framework to handle it, but you might have to do something like this. Okay, so that is the tractability question. The universality question is a different thing. And here I'll just sketch a few things that Ding-Yu did in separate work. So what he did at Stock last year is gave an approach to this this universality question where instead of, you can get universality by sampling, because once you sample the points, you can evaluate any function on those samples. The way he approached universality is he says, I need to come up with a single sketch that can estimate every basis moment simultaneously. And if I can estimate every basis moment simultaneously, then I can estimate linear mixtures of them. Okay, and through this you can, generate a universal sketch. Okay, so I won't say too much about that, but here's some really nice, pretty pictures from his other paper where if you want to do the function that is 1 outside of 0, the indicator function here, then this is we can represent it arbitrarily finely with this 1 minus cosine basis. Absolute value, you can do another cosine decomposition. Log 1 plus absolute value of z, same thing. So here are some conclusions. So the definition of tractability is a little more subtle than it should probably be. So everyone who's studied this problem said we're only thinking about functions where the components of the vector are integers. And we're mapping integers to whatever the function is, reals. If you look at functions that map reals to reals, and then you assume some reasonable assumptions on precision, like every update is log n bits or something like this, the definition of tractability actually changes. Okay, so this function is tractable, x squared log 1 plus x, if you're dealing with integers, because this log term is small. Okay, and it's intractable if you're dealing with reals, because when you make x get close to 0, this function starts looking like x cubed, and you can basically, if you want to do, third moments, you can compress everything to the range between, 0 and 0.01, and then you can recover from that an estimate of the third moment. Okay, so there's some subtleties here in the definition that, might need to worry about. Okay. So, okay, here's our conjecture. If f is tractable, and by this I mean pick either definition you want. I think it's true for both. Then the LP approach that I sketched out, I'm saying should work for any function. Okay, so you should always be able to find a good approximation such that the ratio of g plus and g minus is polynomial in 1 over epsilon and log n times the actual function. And if this is true, then this sort of, is the final answer to the tractability question. And if it's not true, then it's obviously not the answer. So, or maybe it's not the, I don't know if there's I don't know if a negative version of this conjecture kills the whole inner thing, or maybe it just says you need to do something else, but this would be sufficient to characterize the class of tractable functions. Okay. That's all I have.
Questions? I have a question. So, I guess the ability to sort of add and subtract things seems to be causing a lot of, I guess, so this tractability is, a lot in the turnstile model, right? So this is more
yeah.
general. Things can go, and are more things tractable if you make more assumptions about the kind of changes that can happen to the vectors?
Well, what do you have in mind? Besides incremental and turnstile, do you have any other thing in mind?
Well, so for example, how about incremental?
So in the incremental model, you don't, as far as I know, you don't get anything more, but sometimes you can do things simpler and slightly more efficiently. But we're talking log factors.
So it's really not. My first gut think would be that once you can add and subtract, now this sort of issue with zeros is a big problem. I guess what you're able to do is to separate those out. So I'm surprised it doesn't cause more problems.
Yeah, so I think you can artificially create similar, like one of the things with the nearly periodic function is you can make it get arbitrarily close to zero. It's never zero, but you can make it get polynomially close to zero. If you could manufacture functions that get exponentially close to zero or something like that, that would probably screw things up. And those would not be tractable. If when you get that close to zero, that's not a periodic pattern. If it's periodic, then it's fine.
Do you know? I guess these are all cases where what you want in the end is a number.
Yeah.
I can imagine situations where what you want is kind of a function, like these are data points that are being fed into some learning algorithm, produces something, and then as we add or subtract data, we want to know what would the result of the learning algorithm look like, if as we add or take data out of our data pool, and we want to be able to. It's one thing to add data, then maybe I want to, this person didn't want their data in there, I want to take it out, and I want to quickly update, the result. You have like this, does anything carry over? Does that seem that's something that people, talk about a lot of
Yeah, I don't know what, if you can apply a pretty interesting class of functions, to these sketches, aside from this sort of, summation, essentially. Anything more exotic than that. There's pretty hard constraints on this. As soon as you want to do anything interesting, it's just like, it's virtually impossible to prove it.
Yeah, so how would the impossibility results look like here? Like how would you prove X cubed cannot be sketched?
Reductions to various communication complexity problems, set disjointness, things like that.
And this can be proved for any exponent which is larger than 2?
That's right. Yeah. So the correct bound is n to the 1 minus 2 divided divided by p. That you can get that within a log factor basically.
So you can think n to the
N to the 1 minus 2 over p, where p is the p moment. So as soon as p is larger than 2, you have some polynomial matching upper and lower bounds.
And do you see that kind of like a low bound technique can be extended to this general like a Khintchine?
I mean, that lower bound technique is not assuming anything on the form of the sketch.
Yes.
It's just saying this. If you can solve this problem, you can.
But maybe I'm asking why like this exponent of this Levy process cannot have a degree higher than 2 has any connection to the communication low bound, saying that if you want to like polylog space, you have to.
Yeah, I don't think it's gonna. I think basically sketches give you Levy processes.
Okay.
I think there's a much more. There's some theorem there to be proved that basically says whenever you see a sketch, it's implicitly there is implicitly an infinitely divisible distribution somewhere, and infinitely divisible distributions give you Levy processes.
Okay, but that's a conjecture, right?
Right, this conjecture. I mean, I don't know if it's true. I'm just saying that's the that's basically what you'd have to show.
Okay.
But these lower bounds, they don't presume any form of the sketch. There's no algorithmic assumptions at all.
All right, thanks.